Hello and welcome to this video on finding the coordinates of a vector space element with respect to a given basis, or just finding the coordinates of a vector with respect to a given basis, right? A vector space element is a vector from that space. So in this video, pardon me, I will be defining, what are the coordinates of a vector relative to a basis B, or with respect to a given basis B, or whatever the basis name is. And also I'll define what are the what's a coordinate vector of a vector from a vector space relative to a certain basis or with respect to a certain basis. And I'll go over several examples where I'm given a basis for a vector space, a vector in that vector space, and then asked to find these coordinate vectors. Okay. So here I have a page on coordinate vectors. So suppose we're given a vector space V. It could be Euclidean space, or that those spaces of polynomials of degree 3 or less, or 4 or less, or whatever, or just spaces of matrices. And a basis for that vector space called, I'm calling it B here. And say this basis contains vectors u1, u2, u3, all the way up to un. Alright, so the dimension of vector space B would be, n dimensional. Right. Now remember what it means real quickly for a set of vectors to be a basis for a vector space. It means that it spans the vector space, right? So every vector in V should be able to be written as a linear combination of these vectors in the basis. And these basis vectors are linearly independent. Alright. So yeah, and that's what I'm saying here, right? Each vector V in the vector space V, so this is lowercase v, the vector V with the little arrow above it. So each vector in the vector space can be expressed uniquely as a linear combination of the vectors in the basis, right, in B. And that's what I'm saying here. So vector V, this is, again, any vector from the vector space, should be able to be written this way, as a C1 times U1 plus C2 times U2 plus plus all the way up to Cn times Vn, where this C1, C2, Cn, all of those are the coefficients of the vectors are scalars. They're, if a particular scalar set isn't mentioned, we'll just say the real numbers. So these are real numbers, C1 through Cn. And all these scalars, these coefficients of the vectors, in that order, right, in the order of U1, sometimes they refer to this as an ordered basis because we're going to look at the vectors in that particular order. The coefficients in that particular order, those scalars, are called the coordinates of vector V, relative to basis B, or you could say with respect to basis B. Same thing. All right. So yeah, so it's kind of that simple. We've actually done this in other videos before. If you're given a vector and a set of vectors and asked to write this, write this vector as a linear combination of that set, the scalars that you find, right, the weights, remember these are called the weights, the C1 through Cn. The weights of the linear combination are also referred to now as the coordinates of the vector. And then once you know the coordinates, forming what's called the coordinate vector of the vector V relative to or with respect to basis B, the coordinate vector of vector V relative to basis B is denoted this way. It's like a little matrix symbolism. right? Little brackets on this either side of the vector. Then there's a subscript where, you know, this is the basis down here, basis b. So it's the coordinate vector of v with respect to basis b, or relative to basis b, equals, and then you just have a column vector. And in this column go those scalars, right? Go the coordinates, the c1, c2, cn, in the correct order, right? Make sure they're in the correct order. You know, so the first scalar will correspond to the u1. The second scalar will correspond to, you know, vector 2, u2, and blah blah blah. The nth one here will correspond to that should be un, shouldn't it? I wrote vn earlier, didn't I? That should be un. They're all u's. But this so this nth scalar should correspond to the coefficient of the nth vector un from the basis. All right. So, for example, got several examples for the rest of the video. All right. So the first one, I have some pictures associated with it because we're going to be in R2. Remember, in R2, that's two-dimensional Euclidean space. Under the standard operations, you know, standard vector addition, standard scalar multiplication, we can very easily picture things, draw pictures on the, you know, the XY plane. Pardon me. So here are a couple bases for R2. You know, this one's the standard. I'm calling it S. It's the with vector 1, 0 and 0, 1. You know, this is the standard basis for R2. In some texts, I've seen this given a special symbol. You know, the standard basis with like a little fancy E-looking thing with a subscript of 2. I think that's a Greek letter eta or something. Don't quote me on that. But I'm going to call this S just for standard basis. All right, so that's the standard basis for R2, 1, 0, 0, 1. And then I've got this other basis B. This is this set of vectors with 3, 2 and negative 2, 5. This is also a basis for R2. Remember, a basis for a vector space is not unique. A vector space will have many, many bases. Pardon me, wow. Alright, I apologize, that was probably pretty loud. Alright. Okay. So now we're given a vector, v, from R2, right? A vector with two components. Say v is the vector with two components, 5 and 16. Right, and this belongs to R2. And what I'm asked here to do is, you know, let's find the coordinate vectors of v relative or with respect to the standard basis. So this, you know, little block around v with the subscript of s, and find the coordinate vector of v relative to the other basis, b. All right, so again, the little brackets around v with the subscript of b. All right, so I'll do each one of these separately. Now, with respect to the standard basis for a vector space, and really any vector space, not just R2, when you're writing the coordinates with respect to the standard basis, it's pretty simple. All right, so remember here, you know, v is 5, 16. And let's do the standard basis first. Right? Standard basis for R2 that had the 1, 0, 0, 1. And if I'm trying to find the coordinates or the coordinate vector, right? In order to make that coordinate vector, you need the coordinates. You need the weights of a linear combination. So we're trying to find, you know, say C1, which is a scalar, and I'm using C's here instead of A's like in previous videos because, you know, they're coordinates now, all right, a C for coordinate. So I'm trying to find C1 and C2. Again, two of these because there's two vectors in the basis, such that, you know, C1 times the first vector in the basis plus C2 times the second vector in the basis 0, 1 is equal to V, right, 516. All right, now these are all nice, vectors from R2, scalar multiplication, vector additions, very simple. If you were to do scalar multiplication and vector addition over here, this would be, C1 plus 0 C2, so C1 in the first component, and then 0 C1 plus 1 C2, so C2 in the second component. And you can very easily see that it's obvious that the value of C1 needs to be 5, and the value of C2 needs to be 16. All right, so these are going to be the coordinates of V with respect to or relative to basis S. Right, this basis I called S. So that means because remember the basis vectors are like the building blocks for a vector space. So if I take these two vectors, what I'm asking is how can I use these two vectors to build this vector, right? To create this 516, and these coordinates kind of tell you how to do that. All right, we have 516. Right, is very clearly equal to 5 times that first basis vector, 5 times 1 0, plus, and then 16 times that second basis vector, 0 1. All right. So again, you say that 5 and 16, right? What are the weights of the linear combination? Are the coordinates of V relative to basis S. And then now that I have these coordinates, we can talk about making the coordinate vector. The coordinate vector of V relative to S. That's denoted this way. And it's just a column vector, right? Which in the first position, in the first component of the vector, is the first coordinate, right? The scalar that's multiplied by the first vector in the basis, so 5, and the second component is the second coordinate, 16. Right. Okay, so that's part 1, right? And again, while this is telling me that I just take 5 of the first vector, add 16 of the second vector, and I get the vector in question from R2 there. All right, so let's see that happening in a picture. All right, here's R2. All right, here's R2. It's the R2 with the standard basis 1 0 0 1. I call that S, right? Got horizontal axis, vertical axis. These are the spans of those two vectors. Right, these axes are just every scalar multiple of 1 0. Right, you got 1 0, then 2 0, 3 0, 4 0, then negative 1 0, negative 2 0, negative 3 0, negative 4. The span of these basis vectors create the axes for my R2, for my space. And then 0 1, 0 2, 0 3, 0 4, 0 5. 0 negative 1, 0 negative 2, 0 negative 3, 0 negative 4, and so on. Right. The vertical axis is just the span, right? This all scalar multiples of 0 1. All right, so you see 516. All right, remember I mentioned I drew it as a position vector. So from here to that's 5 16, right? Over 5 up 16. Well, remember I mentioned the coordinate vector here is also 5 16. So that means I take 5 of these. If I start from the origin here, I start drawing position vectors. I take 5 of these, the first vector in the basis. So there's 1, 2 of it, 3 of it, 4 of it, 5 of those 1 0s, and then add on, right? add on 16 of the second vector from the basis. So I add on 16 of these, right? And 0, 1 is just 1 unit, pointing 1 unit up. There's that vector, 0, 1, and then 2, 3, 4 of it, 5 of it, 6 of it, 7 of it, 8, 9, 10, 11, 12, 13, 14, 15, and 16. You see I create the sum of these vectors, 5 of that first vector plus 16 of that second vector would have a resultant vector of this green vector here. That's vector v, the 5, 16 that I was given. All right. Okay. Yeah. And do you see how too, like, when you look at graph paper, see all the grids are made up of, little blocks of these vectors. There's a vector, 1, 0. There's vector 0, 1. Here's the opposite of 1, 0. Here's the opposite of 0, 1. You can say that every block, every part of the grid, every square here is, surrounded, is made up by, these two vectors, these two basis vectors. So you see it spans, those two span the space. But there, so that's what the standard base is. That's what you're used to, right? You're used to that. When I draw the vector 5, 16 in, I just go 5 units to the right, 16 units up, and I've got that vector created, with 5 of 1, 0 and 16 of 0, 1. But, this isn't the only basis, right? This is not the only basis for R2. So the other basis I had, the other basis I had was this one here, basis B, right? With the vectors 3, 2 and negative 2, 5. So what are the coordinates of this vector with respect to this basis? So the question really is, how much of this vector plus how much of this vector would make this vector? All right, so how do I use these as building blocks, right? These are a basis for R2. These are building blocks. How do I use these to construct 5, 16? All right. So this time, I'll just keep this up here and get rid of the standard basis. There we go. So what I want is, I want to find the coordinates, right? And then again, there's two vectors in the basis, so I'm going to find two scalars, C1 and C2. Such that, a linear combination of these two vectors is equal to the vector in question, C1 times, 3, 2, plus C2 times negative 2, 5. Equals this vector in question, right, the 5, 16. Now performing the scalar multiplication and vector addition, we get a vector from R2 again, where the first component would be 3C1 minus 2C2. The second component would be 2C1 plus 5C2. And I want this to be equal to 5, 16. So what we actually get here is and I should have done this earlier. All right. This is actually a system of equations right here when I did this earlier, but it's an easy to solve one, right? Because C1's 5, C2 is 16, it has to be. But this is still a system of equations, a system of linear equations. And so when we do this, when we go to find coordinates, of a vector with respect to a certain basis, you'll always be able to set up eventually, right, in the process of it, you'll be able to set up a system of linear equations. And let me show you that system here, and you can probably see it, right? In order for this vector to be equal to this vector, I'm getting the following system, right? Involving C1 and C2. 3C1 minus 2C2 would have to be equal to 5. And 2C1 plus 5C2 would have to be equal to 16. All right, now there are many ways we have seen to express or represent a system of equations. I could represent this as a matrix equation, where I have three coefficients of C1, 3, 2, and coefficients of C2, negative 2, 5. There's a coefficient matrix times the variable matrix with C1, C2 in the correct order, equal to 516 over here. Okay, and I'll come back to this in a minute. All right, well, maybe more than a minute, but I'll come back to this thing here to explain how you could actually construct this kind of a matrix equation right away from the very beginning of the problem. A little shortcut later. Or we could set up a little augmented matrix, right? We have 3, 2, negative 2, 5, and then the equal, and these are coefficients of C1, coefficients of C2, equals sign with the bar, and then 5 and 16 on the other side. All right, and then I would go about putting this into, using raw operations, putting this into reduced echelon form, or even just row echelon form, regular echelon form, and solving by back substitution. But it's I'm gonna go to the calculator. I know it's only 2 rows, but I don't want to do all the writing with the operations, and you can do it by hand if you want. But so I'm going to take this here, and we'll go to that reduced echelon form or reduced row echelon form, RREF, and see if we get any solutions to this, right? Because if there are, I mean, there should be, because we said that that set B was a basis for R2, so every vector in R2 should be able to be written as a linear combination of the 2 vectors from the basis. Alright, so I go to the matrix calculator here. This is 84 plus, to the matrix menu, edit matrix A. This is a 2 by 3 matrix I'm looking at, right? The whole thing, if I consider both sides of the bar. So a 2 by 3 matrix, 2 rows, 3 columns. First row 3, negative 2, 5. Second row 2, 5, 16. Then I get out of here, go back to the matrix, over to math, and then that reduced row echelon form. And I want to put matrix A into reduced row echelon form. Alright, and there we're getting some solutions, right? You get 1, 0 for the first column, 0, 1 for the second column, and then you got 3, 2. So this is telling me that C1 must be 3, and this row is telling me that C2 must be 2. And here are the coordinates. The coordinates of V, but this time relative to basis B, not basis S. Relative to basis B. Alright, so that means that, if I go back to the basis B again, sorry about the cluttered paper here. So if I go back to basis B, there it is there. That means that 3 of the first vector plus 2 of the second vector will give me this vector from R2. Right? And we can double check this, right? Take 3 of that first vector plus, and then 2 of the second vector from the basis. Will that be equal to 516? Well, yeah, 9 plus negative 4 is 5, and then 6 plus 10 is 16. It does work. All right. So 3, 2 are the coordinates, and then we would say that the coordinate vector of V relative to basis B, alright, this little, again, the brackets, and then I put V in here. Remember, V is this 516. So I mean, you could also write, it would look kind of silly, but here it is at the double, I got the brackets around the vector, right? The vector is 516, so I got the brackets around the vector, and then with basis B as a subscript. So this one's a lot easier to look at, right? Because no double brackets and all that. Would be equal to, and again, the components of this coordinate vector are the coordinates in the proper order, right? The coefficient of the first vector of the basis, and then the second component, the coordinate or the weight of the second vector in the basis, so 3, 2. Alright, so what this is telling me is that for this basis B, right, using the vectors of basis B, 3 of the first vector in the basis plus 2 of the second vector in the basis would give me this vector inside the brackets here, would give me vector V. Alright, now I did draw a picture earlier. Remember what the standard basis. Alright, remember what the standard basis. This was with basis S. To get this vector 5, 16, I took, 5 of the first vector and then 16 of that second vector added on to give me the resultant vector of 5, 16 to give me this green vector here. Well, that was with the basis 1, 0, and 0, 1, right, where the axes were horizontal and vertical. But if you have a different basis for R2, you're creating a different grid system. Right, like I mentioned earlier, all the grids here, all the boxes, all the boxes on this grid have a horizontal component of 1, 0 and a vertical component 0, 1. They're little 1 by 1 squares, little 1 by 1 grid pieces. But if the basis is a different set of vectors, then the grid system looks completely different. But it's still R2. It's still the plane R2. And here's what I have here: the basis B. This took a little while to draw. Alright, this is basis B, right, with vector 3, 2 and negative 2, 5. So here's the origin. Alright, here's where I started everything from. And then see my one-axis, the thick line, is going in the direction of vector 3, 2. So is not going in the direction of 1, 0 like the x-axis does. So one of the axes goes in the direction of 3, 2. And every time I go, over 3, up 2, over 3, up 2, every time I go one of these vectors, 3, 2, that's 1 unit. That's, just like back on the xy plane, whenever I go one of these 1 zeros, that's 1 unit, 1 unit, 1 unit, 1 unit, 1 unit, right? And whenever I go a 0, 1 in the up and down direction, it's 1 unit, 1, 1, negative 1, negative 2, negative 3, right? But the axes are different here. One is the span of 3, 2, and the other is the span of negative 2, 5. All the scalar multiples, and that's this other thick line here, where again you go left 2, up 5, left 2, up 5, and every time I go negative 2, 5, every time I go in the direction of that vector, every time I get another one there, you see that's 1 of that vector, 2 of that vector, 3 of that vector. And you see the new grid system? Instead of the old one where every box was just a little 1 by 1 unit square, now every box in this grid system, where the basis is these two vectors, is like these these parallelograms here. Right? Every single grid box is made up of a 3, 2. Right? There's a 3, 2, and there's a negative 2, 5. Right? A 3, 2 and a negative 2, 5, a little parallelogram. Right? So a totally different coordinate system than the original XY plane. And this will happen anytime the basis changes. Right? So standard basis, you're used to that. You've been used to that since elementary school, elementary algebra. But now the basis changes, and it changes the grid system. It changes the way you look at the plane. It's still the plane, right? It's still R2. And what I've drawn here is the same vector as earlier. Right? So you see how look at the green vectors there. They're the same exact size, same direction. Right? That's the vector 5, 16 again. So I have drawn the vector 5, 16, starting from the origin, right, over 5, up 16, if I was doing the standard stuff. Right? There's that same vector I drew on the previous page. But now we're trying to figure out where are the coordinates of that vector with this basis. Right? And again, you're just going to, looking at this grid line like say this point over here. That would be negative 1 of that, negative 2 of that first vector, and then 1, 2 of the second vector. So this has coordinates, negative 1, 2, if you think about it, almost like the XY plane. This point over here. is 4 of the first vector and then -1 of the second vector. So this has coordinates. I'm just drawing it like the XY plane where you have points. This is like 4, -1 on this new coordinate system, right? And I know it's a little funky because you're like, hey, 4, -1, 4, -1, that was 1, 2, 3, 4, that was here, right? 4 down 1 from the origin. Well, I still did that. You know, here's 4, -1 when my bases vectors were the standard basis. But I still did that. I went 4 of one vector, right? 4 of one vector from the origin, and then -1 of the other vector, and got another, you know, this point 4, -1 with these new coordinates. Okay. So do you see this vector 5, 16 that's drawn again, the same vector as before? See how I'm going to get to that point to create this vector. See how I go 1, 2, 3 of this vector. There's, you know, 3, 2, and then 3, 2 again, and 3, 2 again. There's 3 of that vector, and then going in the direction of -2, 5, the other vector, there's 1 of that vector, and then another one. So the coordinates of this vector with this basis, right, with respect to this basis is 3, 2. 3 of the first basis vector plus 2 of the second makes that 5, 16 again, which is what I said back here, right? That's what this means. So 3 of that first vector in basis B, 3 of this 3, 2, plus 2 of this -2, 5 makes the vector 5, 16 yet again. All right, so, and hopefully this picture helped. All right, it took a little while to draw it. You might be able to tell these are all drawn. But when your basis is other than the standard basis, you get a different grid system than what you're used to, like on graph paper. Right? Graph paper is the typical grid system that you're used to, where every square is a 1 unit right, 1 unit up square. Right? But that's not always the case. You know, you can have any basis you wish for R2 and create a whole new grid system like I've done here, and find coordinates that way. Alright, now those will be the last drawings I show you, where you see it takes a while to draw those things, and maybe I'll look for a website that actually draws nice little grid systems for you, but didn't really search for anything before I started making this. I just thought I'd draw it out. Alright, so let's keep going with this. Alright, so now for the rest of the video, I'm going to be doing the following. Alright. For the rest of the video, I'm going to be doing the following. I'm going to be finding the coordinate vector. All right, finding the coordinate vector of vector v from some vector space relative to or with respect to basis B. All right. So here, I'm still in R2. All right, still in two-dimensional Euclidean space, and again, I didn't draw this one out. You could draw, if you wanted, like I did in the last page, you could draw your own grid system where these two are the basis vectors instead of 1, 0, and 0, 1. Alright, so again, I'm going to try to find the coordinates. Now, what that means is I want to find, you know, there's 2 vectors in this basis, so I want to find 2 scalars, C1, C2, such that C1 of the first vector, right, so C1 times 0, 2, plus C2 of the second vector of 6, -2, is equal to the vector from R2 that we have, right, is equal to -3, 2 there. Alright, and then can you see how this leads me to a system of equations, right, involving C1 and C2? Where I have no C1 plus, you know, 6 C2 equals -3, right, the first components, and then 2 C1, then minus 2 C2 must be equal to +2. Right. Now I think it's obvious to solve, you know, it's pretty easy to solve this one. You know, the C2 would have to be, right, C2 would have to be -1/2, and if C2 were -1/2, multiply that by -2, that's +1 and I would subtract 1, get 1 over here, and then divide by 2. C1 would have to be positive 1/2. And there we go. Here are, this isn't the answer. That's not the coordinate vector yet, but it's pretty close. You're almost done. But these are the coordinates of V with respect to basis B. All right. I need half of the first vector, and I need negative half of the second vector to make this vector from R2. Now, let me show you again how. Remember how you could write this as either a matrix equation, where you have the coefficients of C1 down the first column, coefficients of C2 down the second column, then times the variable matrix, right? C1, C2 in the proper order must be equal to this vector of constants on the other side, negative 3, 2. Or you could write this as an augmented matrix. Just showing you alternatives, right? Where again the coefficients of C1 down the first column, coefficients of C2 down the second column, little bar, and then negative 3, 2 on the other side here. And try, put this in. Now again, you don't really, this is already an echelon. Well, if you just switch rows, it'll be an echelon form, and you can solve it by back substitution like I did. You could show either way. Now, what do you notice though? All right. What you're going to notice is that this coefficient matrix, right? This matrix here, same thing with the left side of the bar and the augmented matrix. See how these are just made up of the vectors from B, from the basis 0, 2, 6, negative 2, 0, 2, 6, negative 2. Pardon me. The vectors from the basis will make up the columns of this coefficient matrix, and then the other side is just the vector that we're trying to create, right? With these basis vectors, we're trying to create negative 3, 2. So negative 3, 2 on the other side. Here, negative 3, 2 on the other side of the bar. All right. Now it gets a little trickier when we're not in Euclidean space. Okay. But when you're in Euclidean space, it's very simple. All right. I'm going to write out a more general version of that later. And same thing happened earlier, in one of my earlier examples, right? These coefficient matrices were just the vectors from the basis, and then that 516 was the vector we were trying to create, right? Trying to construct. All right, so now we solved it already, and great. So a coordinate vector, right? This will, with respect to basis B. All right, so the coordinates of vector V with respect to basis B is this vector here, where again the first component is 1/2, second component is negative 1/2. All right, and double check. Take half the first vector. Well, half the first vector would be 0, 1. Negative half times the second vector would be negative 3, 1. And 0, 1 plus negative 3, 1 would be negative 3, 2. So these are correct coordinates, the correct weights, and tell you how to construct this vector from these two. All right. Okay. Going back to this little system I set up here with the matrix, here's something you might see written as well in some texts. Looking at this system, you can think of that coefficient matrix as, you might see it written as MB, M sub B, times, and then the C1 and C2 are the coordinates. So C1 and C2 here, this matrix with the C1, C2, that's your coordinate vector. So times the coordinate vector for V with respect to B is equal to, and then this is vector V over here. Right. Where the columns of MB are the vectors in B. Alright, now I will say this, that this is only true for Rn, for Euclidean space. There's a very similar version of this when we get to different vector spaces, just general vector spaces. But if we're in Rn, like we were in R2 here, you can very simply set up a system, set up an equation that you need to solve, and then find your coordinate vector with respect to B or relative to B this way. All right. And even if you'd like, and I'll show you with the next couple examples, another way we could find the coordinate vector. All right. Okay. So next example. I have the vector 3, -4, 7. That's 3 components. That's from R3, another Euclidean space. And the basis this time, B, is the standard basis for R3, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, right? All the columns of the 3 by 3 identity matrix. All right, the standard basis for R3. Now, I think I mentioned this before, right? Before I went to those pictures on the XY on the graph paper that I showed you. When you're trying to find the coordinates relative to a standard basis, it's really simple. So again, what we're trying to do is we're trying to find, there are 3 vectors in the basis this time, so C1, C2, and C3, such that C1 times 1, 0, 0 plus C2 times 0, 1, 0 plus C3 times 0, 0, 1, right? This linear combination of the basis vectors is equal to V, is equal to the vector from R3, 3, -4, 7. Now, I hope it's obvious that C1 needs to be 3, C2 needs to be -4, and C3 needs to be 7. I hope that's obvious, that these are the coordinates. All right, those are the weights that remember that little thing, I'm in R3 here, so I can use that little MB thing and times the coordinate vector with respect to B will be equal to V here. I could set up this equation where MB is just the identity matrix, right? The first column's the first vector, second column's the second vector, third column's the third vector from the basis, times this coordinate vector equals, and then the vector over here, the V that we're trying to construct, 3, -4, 7. And this is the identity matrix, right? So remember, the identity matrix is just, when you multiply it by any other matrix, it's just that matrix itself. So the coordinate vector for V with respect to this basis is 3, -4, 7, right? Which, like I said, we already knew that. We kind of figured that out over here with the coordinates. So that just means that in this basis B, using these basis vectors, I take 3 of the first one, add -4 of the second one, add 7 of the third one, and I will have constructed this vector that we were given. All right, so yeah, real easy when it's the standard basis. All right. Now, when it's not the standard basis, right, like you saw with R2, it's not as simple. Again, you have to solve a system. Alright, so here I'm trying to find, find my coordinates. I want to solve this equation, C1 times 1, 0, 1 plus C2 times 1, 1, 0 plus C3 times 0, 1, 1. I'm trying to use these basis vectors to construct this vector from R3. 2, 3, 1. Alright, so don't forget, I could write this as this matrix equation, where the matrix with the coefficients are going to have the columns that are these vectors here, 1, 0, 1, 1, 1, 0, 0, 1, 1, times my, C1, C2, C3, but the matrix with C1, C2, C3 is that coordinate vector, right, with respect to basis B. This is the C1, C2, C3. Will be equal to, 2, 3, 1. Or I could set up this augmented matrix, right, with the 1, 0, 1, 1, 1, 0, 0, 1, 1, and then a bar with the equals, and then 2, 3, 1. Right? Either way. Right? Now the way we're used to is this one, right? And I could pretty easily put this in reduced echelon form. And again, I'm gonna go to the calculator. Put this in reduced row echelon form. So that's a 3 by 4 matrix. And they're all ones there. I should be able to do this by hand, but don't feel like it. All right, so 1, 1, 0, 2, 0, 1, 1, 3, 1, 0, 1, 1. All right, and then I already have reduced row echelon form entered, so I'll just re-enter it. All right, and we get this 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 0, 2, 1. And there you go. There are the coordinates right here. All right, because this would imply that C1 is 0, C2 is 2, and C3 is 1. All right, so from here I'm getting that coordinate vector with respect to basis B is the vector with 0, 2, 1. All right, so again, what this means is that if I'm using the vectors from basis B and I want to create vector V, I need to take 0 of the first vector, so none of that 1, 0, 1, add to it 2 of the second vector, so I would add 2, 2, 2, 2, 2, 0, and then add 1 of the third vector. So 2, 2, 0 plus 0, 1, 1 would be 2, 3, 1. Yes. All right, now, another way you could do this, right? Remember I called this thing here the matrix, the matrix M with respect to basis B. This is a square matrix, and since this system should have a solution, right? Every vector in a vector space should be able to be written as a unique representation and a unique linear combination of the vectors in a basis. Since this has a unique solution, this should have an inverse. Right? And when you set this system up and you get this coefficient matrix over here with where the columns are the vectors of the basis, this should have an inverse, has an inverse. So I'll call it MB with the little -1 above it, or the inverse of that matrix. So you could find that inverse and then multiply both sides on the left by the inverse. Alright, so let's see what the inverse is. Now again, I'm just going to have the calculator do it. I don't want to, you've seen how to do inverses probably the long way a while back with either adjoining the identity matrix on and putting it in reduced row echelon form, or using the adjoint matrix method. Alright, so I'm just going to go, what is this coefficient? What's this coefficient matrix inverse? All right, so let me go back here, second matrix, and I'm just gonna go into A and matrix. I'm gonna go into A and just make it a 3 by 3 and just get rid of that last column. All right, so now there it is. There's the coefficient matrix. Get out of here, and I want to find A inverse. So I go matrix A, and then the inverse button. All right, little x to the negative 1 there. All right, those are all halves. So there's, 1/2, negative 1/2. I mean, I guess I could pull the half out. 1/2. I pull the scalar out, but let's leave it this way. 1/2, 1/2, negative 1/2, negative 1/2, 1/2, and 1/2. Right? This 3x3 matrix is the inverse of that one. Now I just multiply both sides on the left by this matrix. Multiply on the left, right? Because remember, order matters when you multiply matrices. Sizes matter and all that. By this inverse matrix, and what we're going to get is, this side, I multiply on the left by the inverse, it'll make the identity matrix, so I'll have just the coordinate vector, right, the C1, C2, C3 equals, and then let's see what happens when I multiply the matrix on my calculator screen. I'm going to multiply this matrix by another one, by a 3x1 matrix, right? So I'm going to make this vector V, the 2, 3, 1. I'm going to make that as a matrix. So second matrix, let's make matrix B. I'll make this as a 3x1, and the components are 2, 3, and 1. Alright, get out of here. And I'm going to take my previous matrix and multiply it by, so you see I'm taking my previous answer, this inverse on the left side, times my matrix B, right, that 2, 3, 1, and look, 0, 2, 1. And isn't this, see, it's exactly what I got when I wrote the system as an augmented matrix and put it in reduced row echelon form. So it doesn't matter. It doesn't matter how you do it. Okay. You find the coordinate vector with respect to that basis B either way. Okay. All right. So now let's get into some different. All right, I got some different vector spaces. Those last few examples, I was working in Euclidean space, right? R, R2, R3, R whatever, right? So now, just a second here. All right. So my next example is actually in in the vector space of the 2x2 matrix, a set of all 2x2 matrices. Okay, so but it's no different though. All right, I'm trying to say, hey, here's a vector. My vectors are 2x2 matrices now, and here's a basis. Now this is not the standard basis. All right, if you recall, the standard basis I'll draw it here. For our 2x2, the set of 2x2 matrices, was all the 2x2 matrices where there was exactly one element, exactly one entry was a 1, and all the other entries were zeros, right? So 1 in the upper left hand corner, and then 1 in the upper right hand corner, and then 1 in the lower left, and then 1 in the lower right. Alright, this was the standard basis for our 2x2. Okay, and I'm only bringing this up for a reason that we'll see later when we talk about writing the matrices, when we write the system of equations that eventually comes from this. Alright, so I'm trying to find the coordinate. Now here's a non-standard basis for the set of 2x2 matrices, right? This 2, 0, 0, 3, 1, 4, 0, 1, 0, 1, 3, 2, 0, 1, 2, 0. So again, what we're looking for are, now there are 4 vectors in this basis, right? So we're trying to find 4 coordinates, 4 scalars, C1, C2, C3, and C4, such that the following happens. C1 times 2, 0, 0, 3 plus C2 times 1, 4, 0, 1 plus C3 times 0, 1, 3, 2, and then plus C4 times 0, 1, 2, 0. Okay, so this is a linear combination of all four basis vectors. I want that to be equal to the, I want to make the vector that I was given, right? 1, 3, negative 2, and 5. Right. Well, do you see how this would lead me again to a system of linear equations? And here's what that system would look like. If I look at the first row, first column entries, right, and again I'm using standard matrix addition and scalar multiplication here. This leads me to this system. Look at the first row, first column entries. You have 2C1 plus 1C2 plus 0C3 plus 0C4 would have to be equal to 1. All right. Then look at the first row, second column entries. You'd have 0C1 plus 4C2 plus 1C3 plus 1C4 would have to be equal to 3. All right, then you look at the second row, first column entries. You have 0C1 plus 0C2 plus 3C3 plus 2C4 would have to be equal to negative 2. And then finally, the second row, second column entries. You'd have 3C1 plus 1C2 plus 2C3 plus 0C4 would have to be equal to 5. All right. Now look at the systems of. Now this is a system of equation like I did before. All right, like I did before. I'm going to write these in two different ways. All right, one is a matrix equation. So my coefficient matrix would be, down the first column, the coefficients of C1, 2, then 0, then 0, then 3. Then down the second column, the coefficients of C2, 1, then 4, then 0, then 1. Down the third column, the coefficients of C3, 0, then 1, then 3, then 2. Down the fourth column, the coefficients of C4, 0, then 1, then 2, then 0. So there's your coefficient matrix times the C1, C2, C3, C4. The variables, right, equals the column over here of numbers, the constants 1, 3, negative 2, 5. All right. So what I'm going to point out here, I said that when we were in R2 and R3, remember this coefficient matrix. The columns, when we were in R2 and R3, the columns were the vectors from the basis. Well, that's not exactly happening here. The columns, this column is not a matrix, right? It's not a 2 by 2. This is not a 2 by 2 matrix. But look at the entries, 2, 0, 0, 3, and look at the entries of the matrix, 2, 0, 0, 3. When I go in the order that I wrote the equations in. In fact, what these numbers are, they are the coordinates of these vectors with respect to the standard basis. Right? Think about that. Let me keep the 2, 0, 0, 3 up. Right? And here is this, that standard basis had these vectors in it. Now you see, I need 2 of this, none of this, none of this, and 3 of this to make that. All right, so the coordinates of that 2, 0, 0, 3 with respect to the standard basis, and again I'll call this S for standard basis. With respect to the standard basis would be 2 of the first, none of the second, none of the third, and 3 of the fourth. Right. And then look at this second vector from our basis B. The coordinate vector for, the coordinate vector for 1, 4, 0, 1 with respect to the standard basis would be, I'd need 1 of this, 4 of this, 0 of this, and then 1 of this. So 1 of the first in the standard basis plus 4 of the second in the standard basis plus 0 of the third, and then plus 1 of the fourth. All right, and so on. I mean, there's only 2 left, but so can you see how the coordinate vector for this third basis vector up here with respect to the standard basis would be 0, 1, 3, 2, pardon me, stacked on top of each other, and then 0, 1, 2, 0 for the last one. So the matrix here, all right, sorry, let me put this back up here. So the matrix, the coefficient matrix for my system this time, and I'll still call it I'll call it MB but then with a S like that. Right. So the reason I'm calling it that is because the columns of this matrix, right, the columns of this matrix are the coordinate vectors, not just the vectors, right? Are the coordinate vectors of the vectors in B relative to the standard basis, relative to the standard basis S. All right, and that's huge. All right. So not just that MB like I had earlier. So these are all the coordinate vectors of the basis vectors with respect to the standard basis. Then the C1, C2, C3, C4, that's the coordinate vector for the vector V that we're looking at with respect to basis B that that's what we're trying to find, right? That's the coordinate vector for V with respect to this basis here. How much, C1 of this, C2 of that, C3 of that, C4 of that. Right? Equals, and then the other side again, this is not this is not V, right? Like it was earlier. When we were in R2 and R3, this side here was vector V, but this is not a 2 by 2 matrix. So again, this is going to be the coordinate vector of V with respect to the standard basis. All right. So yeah, so this over here, this is the coordinate vector of V relative to the standard basis. Again, relative to S. Right, where again, that's the standard basis. All right, because look at that. Look at V, and here was that standard basis again. Right. All right. When 1 of this plus 3 of this plus -2 of this plus 5 of this would make vector V. All right. 1 of the first, 3 of the second, -2 of the third, 5 of the fourth in the standard basis would make vector V. All right. So that's and that's a way you can think about it when you want to go to a shortcut. All right. So this down here, this little formula I've got with this matrix equation, this is for when you're dealing in any vector space. All right. right here, this guy, this equation right here. So this matrix where the columns of the matrix, the columns of the coefficient matrix are the vectors in B, but their coordinates with respect to the standard basis, S, multiplied by the vector, what we're looking for, right? The coordinate vector for V with respect to basis B, and that it should be equal to the coordinate vector for V with respect to basis S with a standard basis, right? Not just V. Right, because again, the vectors are not always vectors from Euclidean space. Now there'll be, they might be polynomials or matrices or functions or whatever. Right. All right. Now you could also, right, have done the augmented matrix here. You don't have to do both, right? Where I set up the augment. And again, it's just the same numbers, but this is 2, 0, 0, 3. Coefficients of C1, coefficients of C2. Coefficients of C3, C4, and a little bar where the equals are going, and then the constants on the other side, 1, 3, negative 2, 5. All right, and then and again, however you want to solve this is fine. You could go to this kind of equation. This is a 4 by 4 matrix. It should have an inverse, so I could find the inverse of this 4 by 4 matrix and then multiply both sides on the left, and that would give me my coordinate vector with respect to basis B. Or take this and put this into, I'll just do this, I'll do this on the next page because again I got the calculator up already. And finding inverses and multiplying by inverses, that takes just extra steps. I personally don't like doing that as much. Let's put this in a reduced echelon form or reduced row echelon form. So over here you could find the inverse if you'd like, and it'll help you. But like I said, not my favorite thing to do. All right, so I put that system in a reduced echelon form or reduced row echelon form. I get the following system. All right, so let's keep those numbers up, and I'll enter those on the calculator. So back to that matrix menu. All right, now that there is this is a 4 row, 5 column matrix. So 2, 1, 0, 0, 1, 0, 4, 1, 1, 0. Nope, not 0. 3. All right, then 0, 0, 3, 2, negative 2, and 3, 1, 2, 0, 5. Okay. Get out of here, and I think the last thing I entered was, no, it's not reduced row echelon form, darn. Alright, so back to matrix, over to math, reduced row, again, RREF, not REF, for reduced echelon form. Matrix A there, and voila. Alright, let me change, these are some, I don't know what these fractions are, let me change these to fractions. So math, change to frac. Okay, there we go. But it does have a solution, right? It does have a solution. Pretty crazy solution, but it still has one. All right. So what I'm seeing is, all right, I'm not going to write the reduced solution. I'm just going to say that, I'll just write down what the vector is, the coordinate vector of V with respect to B. All right, we're seeing that C1. Right, C1 needs to be negative 4 31sts. C2 is 39 31sts. C3 is 64 31sts. And negative 127 31st for C4. Alright, so not really cool, right? Not really nice numbers. I mean, they're still good. They're still fractions and whatnot. They work. Yeah, the only reason this happened is because I actually just made this up before I started doing the video. I didn't pull it from a book or anything like I probably should have. Usually book problems, they have some nicer examples with nicer numbers. But yeah, so all this means, okay, and you can test it out. I don't want to because of the fractions and all that. But all this means is that if I look at the vectors in basis B, right, these four matrices here, multiply the first one by negative 4 31sts, multiply the second one by 39 31sts, multiply the third one by 64 31sts, and multiply the last one by negative 127 31sts, and add all those up, I should create vector V. I should make this matrix here. And again, you can double check that if you wish. I am not going to in this video. All right, so lots of stuff going on. So let me show you in the next example. You know how I'll do it the long way after I show you the shortcut. It'll be weird. It'll be different. Like, I'll explain a shortcut. How do I create these systems? You know, either this matrix equation or this augmented matrix for the system. You can make those pretty quickly if you know the columns right away, right? If you know how to take the vectors in the basis B and express them as coordinates, right, as a coordinate vector with respect to the standard basis. All right, so my last example, all right. So this time I'm in that vector space of, remember P2 here? This is all the polynomials of degree 2 or less, right, with the standard polynomial addition and multiplying by a scalar. So I'm in a new vector space this time. Now, as I did with the last problem, what I want to do here is I'm going to put up the standard basis for P2. You may recall this from another video I've made talking about general vector spaces. The standard basis for, you know, the set of polynomials with degree 2 or less. Now you can go from constant to the highest power or highest power to the constant. I'll go highest power to the constant here. Say x squared, x, and 1. Right, maybe on the last video I made it was like 1, then x squared. They're the same set, right? So this is the standard basis for P2. All right, because every polynomial of degree 2 or more, 2 or less, can be written as some number times a constant, all right, some number times 1, plus some number times x, plus some number times x squared. Every polynomial of degree 2 or less can be formed with these three building blocks, right? This is the standard basis for P2. So knowing this, right, what I'm trying to find are, you know, there are three vectors in here. So I'm going to be trying to find three scalars, C1, C2, and C3, that when I multiply this by C1, this by C2, and this by C3, and add them together, I'll get negative 10x squared plus 17. All right. So what's going to happen is I'll jump right to either that matrix equation where the coefficient matrix, again, down the first column, will be the coordinates of this with respect to the standard basis. Make sure you go in this order, right? Now if I went the other order, 1x squared, it would just be the other way around. But you see I've got 4x squareds, 4 of the x squared, plus 2 of the x, plus negative 1 times the 1. Right? So you see how 4 of this first vector in the standard basis, plus 2 of the second vector, plus negative 1 of the third vector would make that first vector in B, that first polynomial. So down in this coefficient matrix, again, down each column will be the coordinates of the basis vectors with respect to the standard basis for that vector space. So then the second vector in the basis, it'd be, you know, negative 3 of that x squared, again going in the same order, plus 1 of the x plus 2 times 1. All right, so those are the coordinates of this vector with respect to this standard basis. And then down the third column, right, I have 1 of the x squared, 3 of the x, and negative 5 of the 1. Right? And then we have multiplied by, the coordinate, our c1, c2, c3, which is the coordinates of vector v with respect to basis b that we're trying to find. And that should be equal to, and then over here again, vector v, but not vector v, right? I'm going to write the coordinates of vector v with respect to the standard basis. So it's negative 10 of this x squared, 0 of the x to the first, and then 17 of the 1. All right. All right, so I'm going to write that same notation I had up earlier, right? Where again I'm calling this that m, taking the vectors from basis b, making a matrix out of them, but I'm taking the coordinate vectors of basis b with respect to the standard basis s. So let's use s for standard basis. And then over here, this is the coordinates of vector v with respect to the standard basis. All right, and then I could find the this should have an inverse. Find the inverse of this, multiply both sides by the inverse, or again, very short way I could write an augmented matrix. So down, same numbers, just without this stuff. 4, 2, negative 1, negative 3, 1, 2, 1, 3, 5, negative 5, and on the equals, and then on this side negative 10, 0, 17. All right, I'm going to do this, put this in the calculator, put this into reduced row echelon form. So, turn this on. All right, that is that augmented matrix is a 3x4. First row 4, negative 3, 1, negative 10, second row 2, 1, 3, 0, third row negative 1, 2, negative 5, 17. Alright, then get out of here. The last thing I entered was reduced row echelon form. Oh no, the last thing I entered was answer to fraction. So I gotta go reduce row echelon form again. Math menu under the matrix RREF, matrix A. Okay. All right. So looks like we're getting the coordinates, right? According to that little, the first row there tells me that the value of the first constant C1 would be 1. Right, the value of C1 would be 1, C2 would be 4, and C3 would be negative 2. So the coordinate vector for V with respect to basis B is this 1, 4, negative 2. All right, and remember what this means. All right, remember what this means. I can write it on the next page, and we can check if you would like. Check on your own. This means that if I took one of the first vector from the basis b, right? If I took one of this first vector from in basis b, it says in the subscript. So I take one of the first vector. So I take just 4x squared plus 2x minus 1, and then add to that 4 of the second vector. So 4 times negative 3x squared plus x plus 2. And then add to that negative 2, so minus 2 times, and then the third vector in the basis, x squared plus 3x minus 5. That should be equal to vector v. Right? That's how I should be able to use these vectors from the basis to construct vector v. That should be equal to negative 10x squared plus 17. We could double check this pretty quickly. Look at the x squared terms. You'd have 4x squared here. Then distributing the 4, you'd have minus 12x squared, that would be negative 8x squared. And then distributing the negative 2, you'd have minus 2x squared, that would be negative 10x squared. And then look at the x terms. 2x plus 4x is 6x, and then minus 6x would be no x. And then the constants, negative 1 plus 8 is 7, plus 10 is 17. It works. So these are the coordinates, right? Of this vector with respect to this basis. right? And this is the coordinate vector of this vector with respect to this basis. All right. So again, like I said, now if that's the shortcut thing I did, all right, the shortcut stuff I did, where I just wrote this matrix equation or wrote this augmented matrix, that's, you can only really write these if you know the standard basis for the vector space you're working in. So I've put up in a video on general, there was a video I did earlier on general vector spaces where I talked about, what is the standard basis for Euclidean space, the standard basis for these spaces of polynomials of degree n or less, the standard basis for spaces of m by n matrices, and that was about it. Right? Those are like the basic vector spaces I went over the standard bases for. So if you go back and watch those, or just look up standard bases for vector spaces, you might come across a list or a chart. But I'd recommend getting to know those, memorizing those, some standard bases for certain vector spaces. Because if you don't know this, right, if for some reason you don't know what the standard basis for a vector space is, then you kind of have to do it the long way, right? And that's what I meant by, I'm going to show you the long way after the shortcut way. Right, the long way would be doing what I did on the first problem, right? Where I take, hey, trying to find the coordinates of this vector with respect to this basis. So that means there's 3 vectors in the basis. So that means I'm trying to find 3 constants, 3 scalars, c1, c2, c3, such that c1 times the first vector, 4x squared plus 2x minus 1, plus, and then c2 times the second vector, the negative 3x squared plus x plus 2, plus, and then c3 times the third vector, x squared plus 3x minus 5. I want to find these values, c1, c2, c3, such that this is equal to negative 10x squared plus 17. All right, and then we do the typical how you multiply polynomials by numbers, distribute, and how you add polynomials together, right? You combine like terms. So if you look at all the x squared terms, right, I'd have 4c1 as the coefficient of that x squared, minus 3c2 as the coefficient of that x squared, plus c3 as the coefficient of that x squared. So combine all of them and you get that as the coefficient of x squared terms on the left side of the equal sign. Plus, and then look at the x terms, x to the first terms here on the left. You'd have 2c1 as the coefficient of that x term, c2, right, plus c2 as the coefficient of that x term, and then plus 3c3 as the coefficient of that x term. All right, and then you look at the constants. You have minus c1 for the constant there, plus 2c2 for the constant here, and then minus 5c3 for the constant there. And I want this to be equal to negative 10x squared plus 17. Now remember, 2 polynomials. Polynomials are only equal to each other if they have the same coefficients. All right. So we get this system where the coefficient of x squared on the left has to be the same as the coefficient of x squared on the right if these are to be equal. So 4c1 minus 3c2 plus c3 must be equal to negative 10. And then the coefficients of x must be the same, so 2c1 plus c2 plus 3c3 must be equal to 0, right? There is no x on the other side. And then the constants must be the same, negative c1 plus 2c2 minus 5c3 must be equal to 17. And look at the coefficients of this. Now I'm solving this system. Look at this, 4, 2, negative 1, 3, negative 3, 1, 2, 1, 3, negative 5, negative 10, 0, 7. Those are exactly what I got back here when I made my augmented matrix. I look down here. See, look at the first row, 4, negative 3, 1, negative 10. 4, negative 3, 1, negative 10. Second row, 2, 1, 3, 0. 2, 1, 3, 0. Negative 1, 2, negative 5, 17. Negative 1, 2, negative 5, 17. So then I get this augmented matrix, and then this solution And there we go. There we have our coordinate vector. One of that first polynomial plus 4 of that second polynomial plus -2 of the third polynomial will give me that -10x squared plus 17 that we were asked for. All right, so if you know a standard basis for a vector space you're in, fantastic. That'll make it that much easier to find coordinate vectors and find coordinates. You'll be able to set up those matrix equations or the augmented matrix for the system. You'll be able to set that up very easily. If you don't, for some reason, know the standard basis for the vector space you're working in, don't worry about it. Just do it the long way. Right? Just figure out, what linear combination, of these vectors in this basis make the vector that I'm asked to find, and then you set up a system of equations from there and solve it. So I mean, either way, you get the same solution, same result. So if you want to use a shortcut, fine. But again, you have to know the standard basis for the vector space you're in. Great. All right, so lots of stuff going on here. I hope you enjoy practicing problems of this nature, getting better at things. Of course, the more you're in reading and watching other videos on by other people, seeing other perspectives. Because the more you're exposed to a topic, the better you get at it. That's usually how it works. All right. And thank you very much for watching.